A concept in calculus that you really got to know is something called continuity. And when you see the word continuity, what comes to your mind? What do you think of? Something that's not broken? Something that doesn't really have any like potholes in it, like you're driving down the road? If you were to have a pencil like this, that's pretty continuous, right? I do that, what happened? It's not continuous anymore. I broke it. So what we want to do, we got this idea of continuity, we got an idea of it. You know, if you have a conversation, is the conversation continuous? You know, we got that kind of idea, but here's the real question. Could you quantify it, calibrate it in terms of mathematics? How could I look at a function and determine, okay, this function is going to be continuous or if it's not going to be continuous? And one of the reasons why we want to look at continuity is there's very, very nice properties associated with continuous functions. And we want to use those properties to help us to understand what's going on with some kind of calculation. If it's continuous, what that essentially means is you can take your pen or your marker, whatever, put it on the board or a piece of paper, and you can move around, go from one spot to another spot without taking your pen or marker off the paper or board, wherever you're working with. That's the idea behind it. And functions, some functions which are continuous everywhere, there's no problems at all, polynomials. If you take a polynomial of degree 2, degree 3, it does not matter. These are going to be continuous everywhere. They're going to look maybe a little bit like this. And again, if one side goes up, the other side goes down, that's going to be an odd degree polynomial. Both sides go up, it's going to be an even degree polynomial. Other ones, exponentials. If you look at, remember the graph for e to the x? That graph looked a little bit like this. There's no holes in it, there's no breaks in it. We're going to be good. Could I describe a function which is possibly not continuous? See, by understanding what it's not will sometimes help me understand what something is. And the first thing I note is, if I had some kind of function, and if I had a hole in it, like that, is that continuous? No, definitely not continuous. Okay, well, what if I had a function then which did something like this? Would that be continuous? Definitely not. Because in order from here to here, I broke something. Just like I had the pencil and it was continuous and I broke it, now it's two different pieces. So this is also not continuous. So in order to be continuous, I got to go from one point to another point, and I cannot encounter any holes or any breaks. And if I can encounter holes and breaks, it's not going to be continuous. Let's say that this function, again, it's not defined at a value for a. I could define it for a value for a, and I can represent that in the graph by just putting a little closed dot. So the dot would then indicate, yeah, you plug in the value for a for the function f of x, you'll get this order pair way up there. So the function is defined. So the very first thing you need for continuity is you have to define the point. If you don't define the point, you fall through it. There's nothing there. You got a break. You got something going on. But just because you defined a point, it does not mean that it's still going to be continuous. Look at the plot. This point is broken. It's way up here. I can't go from here to there without taking my marker off the board. If I'm stuck right here, I can't get up there without saying that. It's like, beam me up, Scotty. It's not continuous when I'm looking at, those kind of issues. So the point, first off, does need to be defined, but I also can't have this. If I was looking at maybe the point again, x equals a, I got a break in the graph. What I need when I have those breaks in the graph in order to be continuous, I need the breaks to go back together. I need to mend it, don't I? If I don't mend it, put the breaks back together, it won't be continuous. So what could I do then to guarantee I do not have those kind of breaks? Well, I can use the whole entire idea of a limit. As you approach from the left and as you approach from the right, if you go to two different locations, up here and up here, you have a break in the graph. So if I want to make sure that I avoid these breaks, I've got to make sure the limits are exactly the same. But just because the limits would be the same from the left and from the right, so I don't have those breaks, it is entirely possible, once again, to have some kind of graph in which, yeah, you are approaching it to the exact same spot, but you're missing something. You got to fill in the pothole. Again, if you were to have a point up here which is defined, it's fine. It is defined for that point now, but what's the problem? Did you fill in the hole? No. So you got to make sure that you fill in the hole. The point has to go right there. Now, think about it like this. You got the limit from the left and from the right. It's going to the exact same spot. And that spot needs to be the function evaluation. The limit needs to correspond to the function value at that point. If it does not correspond to that value, it could be way up here. It could be way down here. The only way you can make sure that that hole gets filled in is if the limit does equal the function value. Okay, so let's summarize. In order for a function to be continuous, the way you conceptualize it, you put your pen on a piece of paper, you go from one spot to another spot without lifting up your pen or your pencil. In order to think about this from a more of a mathematical perspective, so we can add some rigor to it, whenever you have a function which is continuous, there's going to be no holes. And that's what this right here is referred to as. This is known as it is a discontinuity, but it's known as a hole discontinuity. And it's also referred to at times as a removable discontinuity, because you've taken one point and what happened to it? It got removed. It's up here. This type of discontinuity, could you think about what this might be called? Where you got to go from one level to another level to another level. Maybe you're Mario. There's a hat, because Marios wear hats. But how would Mario go from this level to that level? Jump! You got it! It's a jump discontinuity! That's exactly what it's called. You jump to the next level. Okay, so when you have these breaks, they're jumps. And there is one more type of discontinuity. If you're going to have some kind of function that did this, you see how the graph's broken? I really can't go from here to over here. what this is telling me is, as I approach the value of x equals a, this thing is going all the way up towards positive infinity. And as soon as I get there, maybe I can go back around. But am I ever going to get to positive infinity? No, it's going to keep right on going all the way up. So I really can't go from here to here. So this is not really a removal discontinuity. It's not really a jump discontinuity. This is an infinite discontinuity. Okay, but for a function to be continuous, I got to fill in the pothole, and I got to make sure that I don't have the breaks. So I got to make sure that the limit from the left and from the right are identical. So a function, f of x, is said to be a continuous function, and I'll say on a region. We're really talking about intervals, things maybe like a, b, or maybe even a closed interval, maybe like we're going to take the b, but that's what we're referring to. So it's going to be continuous on a region, I'll just call it I, such that anything you pick inside this region, maybe like an a value or something, but whenever you take the limit as x approaches a from the left and from the right, the limit does exist. You're going to the exact same spot. The function is defined at that particular value. It does exist. And the limit is exactly the function value. You got to make sure there's no breaks in the graph. You got to make sure that you don't have any potholes. And you got to make sure that all potholes are filled. So you got to make sure the limit is the same as the function value. Okay. A lot of times this is streamlined a little more compactly, and you'll see it expressed just like this. The limit of f of x, x approaches a, is f of a. When I was a student, I was really confused when I looked at this. So I thought, hey, is that how you actually take limits? Is it really just a plug and play? Only when the function is continuous. If you do not have continuity, you do not have that property. And guys, that's exactly why whenever you take limits of polynomials, it really seems like you're plugging it in, because it's kind of what you're doing. It's a continuous function. There's no holes, there's no breaks, there's no infinite discontinuities with polynomials. The same thing with exponentials. The same thing with sine and cosine. You don't have any of those kind of issues. The time in which you do have those issues, rational functions. If you were to look at the domain for the function, and the domain just refers to everything that you can plug in, look at the denominator. If you were to factor the denominator, you'll see you'll have x plus 1, x plus 3. And also, if you factor the numerator, x minus 1, x plus 1, difference of squares. If you plugged in minus 3, what would happen? The universe would implode. Terrible. Don't do that, because you'll get some kind of number over 0. That's not defined. Okay, go back to pre-calculus. What did we say that this corresponds when looking at the graphs of function back in pre-calculus? Vertical asymptotes. Infinite discontinuity. So we do have a discontinuity, in other words, when you have domain violations, those things naturally come together. Look at your function and see when it's defined and when it's not. Vertical asymptote at x equals -3. So we want to classify the point of discontinuity. We can say it is an infinite discontinuity. But I also have another issue. What's the other issue? What would happen if you plugged in -1 for x? The numerator becomes 0. What about the denominator? 0. So I'm back to those indeterminate forms. But look what happens. You factor it. What happens to the factor? It gets removed. So we have also a removable discontinuity right when x equals -1. So in this case, we had two different types of discontinuities with this given function. Okay, and here we divide out the x plus 1. That's exactly why we called it removable. What happened to it? Removed it from the graph. Okay, let's see if we can graph this. Let's get a good visual on it. Take the limit. Take the limit of this function as x approaches positive infinity, and also as it approaches negative infinity. But if I take the limit as x approaches positive infinity, what is this going to be describing again geometrically? Horizontal asymptotes. Linear term on top, linear term down below. And what happens as x races off towards positive infinity? So I got that indeterminate form one more time. The way I fix this issue is to say 1 over x, 1 over x. Multiply through, use properties of limits, and what happens here as x gets really big? That gets really small. So it says I have a horizontal asymptote right whenever you get close to 1. Okay, and also you can find intercept points. If you're going to be crossing the x-axis, that then means that the function needs to zero out. When will the function zero out? This corresponds to a vertical asymptote when it's 0. So the function is going to zero out when the numerator is equal to 0. So right whenever x equals 1. Like that. And I contend you really have enough information to put Humpty Dumpty back together again. Use process of elimination. It's a vertical asymptote. That means you're either going to be approaching positive infinity or negative infinity. There's no one way or two ways about it. You have to go to one of these two values. If you start down here, or excuse me, start up here, you would have to connect up. The multiplicity of the roots, you guys remember multiplicities, tells you how many times you're going to be crossing the x-axis. Talks about those kind of issues. The exponent's 1, so that means you're going to go straight through the point since it's an odd multiplicity. And if you did this, you have to circle back around to level off. Thou shalt not pass the x-axis again. So that would then say, this is not correct. You have to start from below and level off. Horizontal asymptote. Likewise, if you start down here, you have to get up to the horizontal. Otherwise, guys, it's not a horizontal. So what would happen if you start down below? You would have to cross the x-axis. Should you cross the x-axis? Not here. You can only cross there. So if you can't cross here and the choice down here is telling you to cross it, what can you say about your choice you're making? It's not a good choice. Listen to truth. Listen to logic. Don't do that. So you have to start above and then level off. So there's your graph. And from the graph, you can see really quickly now, there is definitely an infinite discontinuity. This is not defined for the function. And you can also see there's this removable discontinuity. You can't really see it here, but you do have to take it and throw it out. And the way you would represent it on the graph is put that hole right there. So the holes refer to the points you remove, and the reason why you remove it is because you're going to be dividing it out. So whenever you see, in other words, 0 over 0, we're talking about those holes, those removable pieces you take from the graph. And whenever you have a vertical asymptote, we're talking about the other type of discontinuity, an infinite discontinuity. And it's possible, again, to have some kind of graph in which maybe it's broken, and then from there you go ahead and you would see what's happening. A lot of times when you see graphs just like this, when they're broken, they're defined as piecewise graphs. And it's called pieces because you're graphing it in terms of pieces. And just a real quick example. You might have something that looks a little bit like this, where the function is going to be linear whenever x is going to be greater than or equal to 0, but it's going to be quadratic whenever it's going to be less than 0. And when you graph this, do it in pieces. What does the graph of x plus 1 look like? It's a straight line. But it's not defined if it's negative. This only takes on the meaning of this when you have that. So you don't have this, in other words. But when it is negative for x, it takes on that meaning. Now we have the parabola. And I can definitely see if I want to go from here to here, I'm going to have to step up to the next level. So here is an example in which you have a step discontinuity right when x equals 0. Okay, so what you need to know is this. You have to know this three-step definition for continuity. The limit exists, the function value exists, the limit does equal the function evaluation. And all this has been compact into a nice package right here. If you know this, that is usually what you see in terms of continuity of a function at the given point of A. And you also have to know the three different types of discontinuities we discussed: removable, step, and infinite discontinuities. So removable, one more time to summarize, those are going to come about a lot of times when you have rational functions and you have 0 over 0. You remove the factor. The infinite discontinuities, a lot of the times when looking at rational functions, it's due to the fact you're going to have a vertical asymptote. And also, if you have a step discontinuity, that means the graph has been broken. And we look at piecewise graphs, a lot of times they are broken. Okay? What we're going to do next time is dig a little deeper into this idea of continuity and see if I have a graph which is broken, what I can do to actually mend it, put it back together, so I can find the certain values to make those connections. Okay, you guys have a great day. I'll see you next time.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.